Hi, welcome back. Now we are going to continue our discussion about the boundary value problem. Just to remind you, the problem was the following. I had a object suspended from the top and stressed because of its own weight. So what happens is we are systematically going through and we have identified all the boundary conditions. Now we are going to continue. We are up to step 4. Step 5. All boundary points covered. Check. Let's see. So there are 3 surfaces. Bottom, side, top, everything covered. Second thing is, at each point on the boundary I have to have 3 conditions. Check. 1, 2, 3. 1, 2, 3. 1, 2, 3. Now we come to the question of trying to guess the solution. Right? And let us write this down, this also. Step 6. Is there a body force? Yes. And it is B equals rho G in the minus K direction. Okay. Now we come to step 7. Now we are off the track. So up to step 6 you have to do for every problem. Step 7 now depends upon what we can do. Okay. So our idea is very simple. If I drew a free body diagram and if I said that the stress on top sigma equal to rho G L and this distance is Z and this is L minus Z, you can see that roughly speaking the force on the bottom will be equal to rho G times Z times A, where A is the area. Draw the free body diagram and calculate. I'm not going to sit there and do it. You can figure it out. Okay. So this is the net force. So you're expecting sigma equal to F over A, which is rho GZ. And this will be sigma ZZ. Can you see that? So if I drew this portion, sigma ZZ is rho GZ. Is our guess. Okay. Now we are done. We are going to assume that all the others sigma ij equal to 0 for I and j not equal to 3. So let us see if does it satisfy equilibrium. So all I have to do is sigma xx comma, so I have to check sigma ij comma j equal to 0 is that, sorry, plus rho b. So let us write this down in pieces. Sigma xx comma x plus sigma xy comma y plus sigma xz comma z equal to 0. Sigma yx comma x plus sigma yy comma y plus sigma yz comma z is it equal to 0. And then the last one, sigma zx comma x plus sigma zy comma y plus sigma zz comma z plus rho g, and this is a negative sign because it's minus k is equal to 0. So that's 0, that's 0, that's 0. So that means this is 0, that's 0, this is 0. That's met. This is 0, this is 0. This one is rho g z comma z, which is rho g minus rho g, that is 0. So that's also met. So equations of equilibrium are satisfied throughout the body. I told you, satisfying equations of equilibrium is easy. Now let us look at boundary condition. On bottom, I had sigma xz equal to sigma yz equal to sigma zz equal to 0. This is automatically true, this is automatically true, and sigma zz was rho gz, and then z equal to 0, it's equal to 0, so it's met. On sides, we had sigma xx nx plus sigma xy ny equal to 0. No problem, because these two are 0. Check. Sigma yx nx plus sigma yy ny equal to 0. Check. Very nice. And then sigma zx nx plus sigma zy ny equal to 0. Check, because these two are 0. It's very nice. So if you guess the stress field, it's actually easy to check the boundary conditions. The traction boundary conditions are not a difficulty. Okay, and you're thinking, hey, I satisfy the equations of equilibrium, I satisfy the boundary conditions, what else is left? Oh, I must be done, no? Not so, not so fast. I want you to remember that there is no guarantee that it meets the constitutive equations, and that there is actually a displacement for which this is a stress field. Right? So I have to check that. So we will now do the next one. Step 7a and then step 7b. This is now we are coming to the hard part of this problem. Step 7b, find or try to find displacement. So how are we going to find the displacements? This is a fairly serious problem. So first step, find strain. And we know what it is. Epsilon ij equal to 1 over E 1 plus nu sigma ij minus nu sigma kk delta ij. This is Hooke's law. In our particular case, we don't have this. We can actually do this even simpler. Do term by term. It will make your life very easy. It will tell you epsilon 1 equals u1 comma 1 equals sigma 1 over E minus nu times sigma 2 plus sigma 3 over E. So this is gone, that is gone, so that will give me minus nu sigma 3 is rho g x3 over E. Epsilon 2 equals u2 comma 2, which is sigma 2 over E minus nu times sigma 1 plus sigma 3 over E. So this is 0, that is 0, so this will give me minus nu rho g x3 over E. Epsilon 3 is u3 comma 3, which is sigma 3 over E minus nu times sigma 1 plus sigma 2 over E. 0, 0, and this will give me rho g x3 over E. We are not done. We have gamma 1 2 equal to u1 comma 2 plus u2 comma 1 equal to sigma 1 2 over g. Sigma 1 2 is 0, so that has to be 0. Gamma 1 3 is u1 comma 3 plus u3 comma 1 equal to 0. Gamma 2 3 is u2 comma 3 plus u3 comma 2 equal to 0. There. So you have to meet 6 equations for 3 unknowns. U1, U2, U3. Look, if you're going to have more equations than unknowns, the chances of you finding a solution are very small. Okay, you have to be very lucky because you have more equations than unknowns. So there will be some incompatibility. You know what I mean? That is, the equations may not be able to be satisfied. So how do we check this? So to make sure we have a solution, we can solve it, we check the compatibility equations. So notice, this is the role of the compatibility equation. It is just a check. It just tells you you can go ahead and solve. It doesn't tell you how to solve it, but it will tell you that you can go ahead and solve. So how do you solve this? Well, in our particular case, the compatibility equations looks like epsilon ij comma kk plus epsilon epsilon kk comma ij minus epsilon ik comma jk minus epsilon jk comma ik equal to 0. This is my compatibility equation. And you can see that it has 2 free indices, 6 equations to check. You're thinking, oh my god, do I have to check all 6? The answer is no. The reason is, look, every one of them is second derivative, right? Right? Look at our epsilons. They are all linear at most. Can you see that? Epsilon 1 is linear in x3, epsilon 2 is linear, epsilon 3 is linear, these are all 0. So if my epsilons are linear functions, but epsilon ij is linear, so it will automatically satisfy compatibility. So second derivative is 0. So as long as your epsilon ij is linear, you don't even have to worry. You can just say, as soon as I get linear equations for epsilon ij, I'm done. It is just it's just automatically satisfied. So once you've done that, so we now know, therefore we know that there is a solution. How do we find it? Well, integrate the equations. What do I mean? I'm going to say u1 comma 1 equals minus nu rho g x3 over e, correct? So this means u1 equals minus nu rho g x3 x1 over e plus f1 of x2 comma x3. We have done this, right, in one of the homeworks. u2 comma 2 equals minus nu rho g x3 over e, which implies u2 equals minus nu rho g x3 x2 over e plus f2 times x1 comma x3, and then u3 comma 3 equals rho g x3 over e, which implies u3 is rho g x3 squared over e plus f3 x2 x3, sorry, x2 x1, x1 x2. So now you have to find these things. How? By doing the shear strings. So now I'm going to do u1 comma 2 plus u2 comma 1 equal to 0 gives me, if you do this, you will get, let's see, f1 comma 2 plus f2 comma 1 equal to 0. So that gives me equation 1. u1 comma 3 plus u3 comma 1 equal to 0 gives me minus nu rho g x1 over e plus f1 comma 3 plus f3 comma 1 equal to 0, and then u2 comma 3 plus u3 comma 2 equal to 0 implies minus nu rho g x2 over e plus f2 comma 3 plus f3 comma 2 equal to 0. Right? So I have three equations for the three unknowns f1, f2, f3, and you have to find it. The trick, of course, you can start with this, and I did a different version in the previous homework example. So you can go look at that and you'll find a different version there. Now I'm going to show you a trick. First trick is to realize that I can actually rewrite this. I can write this as f1 comma 2 plus f2 comma 1 equal to 0, and then I'm going to introduce g3 equals. I notice that f3 comma 1 gives you this, f3 comma 2 gives you this. So what I'm going to do is I'm going to define g3 equals f3 minus nu rho g x1 squared plus x2 squared over e. Okay, now you will see that I will get equation 2 will become f1 comma 3 plus g3 comma 1 equal to 0, and f2 comma 3 plus g3 comma 2 equal to 0. I got this. If you take that and plug it in here, you will get this back. This is a very clever trick, and if you think about it a little bit, you will see that this is actually a particular solution to this problem, and this is the general solution. This you can integrate very easily, because you can show that this will give me f1 equals a1 plus omega 1 x2 plus omega 2 x3. That's the solution for this. f2 equals a2 minus omega 1 x1 plus omega 3 x3, and f3 equals g3 equals a3 minus omega 2 x1 minus omega 3 x2. That's the solution for this, where a, b, c, omega 1, omega 2, omega 3 are constants. By the way, whenever you get an equation like this, the solution to this is here. So whenever you are finding an exact solution, by integrating the strain displacement relation, you always want to convert it into an equation like this. That's the trick. Takes a little bit of effort, but if you are clever and you can guess the particular solution, you can solve it. So look, there's a lot of clever mathematical guesswork involved. Okay, so remember, in the earlier stages I talked about physical insight, physical guesswork. Now you have to do mathematical guesswork, mathematical insight. That's how it goes. So now I have my full solution. Looks like u1 equals minus nu g x1 x3 over e plus f1, u2 equals minus nu g x2 x3 over e plus f2, u3 equals rho g x3 squared over e minus plus this term, because I really wanted f3, which f3 is g3 plus that, so plus, this is g3, okay, plus nu rho g x1 squared plus x2 squared over E plus G3, and F1, F2, G3 are this. This is my displacement. And what will happen is that the body that looks like this, with all this weight hanging like this, will become slightly curved like that. Right? Of course, I'm drawing you a very exaggerated shape, but basically it will curve up here like this, it will kind of bow down here like this, and these sides will become like that. Right? So it's like holding up a very slight. You can see that if you hold a pizza dough, it will sag like this. Of course, in the beginning, not later, but in the beginning. So that's how it works. Okay. So I've shown you the full solution method for calculating it. The hardest parts are two things. One is guessing the stress. Very easy to find the equation of equilibrium. Very easy to satisfy the boundary conditions or not. If it doesn't work, you will immediately see it. Very hard part is this. Calculating the displacements requires you, if you start out with the stresses, calculation of the displacements may or may not work. If the strains satisfy the compatibility equation, you are okay. If the strains don't satisfy the compatibility equation, you're up the creek. Even if the strain satisfies the compatibility equation, you have to do quite a few steps in order to integrate and find the solution. Thank you.